I'm Olivia Macras, and this is our resistive forces lab report. Our hypothesis is as stated below. The more viscous solution, the smaller the terminal velocity will be, assuming the initial velocity is the same when they enter the solution. This is because the ball bearing will experience a larger viscous force, leading to a larger upwards acceleration, slowing down the ball. In order to test this hypothesis, we measured the average velocities of the ball bearings in different liquid solutions. From the position versus time graphs, we were able to calculate the viscosity and the terminal velocities. We used isopropyl alcohol, vegetable oil, and cornstarch. Our independent variable was the viscosity of the liquid, while our dependent variable was the terminal velocity of the ball bearings. Here are some background definitions for this lab. So more background information. The purpose of this experiment was to use liquids with different viscosities to see how that affected the ball bearing's terminal velocity. During the terminal velocity, there is no acceleration, so the net force is zero. This means the force acting upwards on the ball bearings and the force acting downwards are equal. This is important because once terminal velocity is reached, the viscosity can be calculated. Viscosity and macroscopic friction are both resistive forces, meaning they act in opposition to the applied force, or the force of gravity. Viscosity deals with liquids at macroscopic level and is affected by how close or how far the molecules are in relative to one another. Here's our system schema and force diagrams of the ball bearings. Notice that the force diagrams of the ball bearings is before reaching terminal velocity and at terminal velocity. For our methods, we used 3 50 milliliter graduated cylinders and filled them with 3 different liquids. The liquids we used were isopropyl alcohol, corn syrup, and vegetable oil. 3 ball bearings were dropped from the top of each of the 50 milliliter graduated cylinders, and videos were taken of the ball bearings during their entire descent down the graduated cylinder. These videos were then analyzed using the tracker software. We took measurements. Once the videos were focused, we used the tracker to quantify the motion of the ball bearings. We used tracker to track the movements in the y direction. The data collected from the program, we were able to calculate the velocity vectors. In order to calculate the average velocity, we did the change in displacement over the change in time. For the average acceleration, we used the slope of the velocity graph, or the change in velocity over the change in time. For our viscosity, we used force viscosity to calculate this by using mass times gravity equals -6 pi times the viscosity times the radius of the ball bearing times the terminal velocity. The terminal velocities were calculated using the slope of the position graph. The reason we used the slope of the position graph was because all of them were nearly linear, thus leading us to believe terminal velocity is reached because the slope stays a constant, indicating the constant velocity and no change in acceleration, therefore no net force. Average acceleration was also calculated using the slope of the velocity graph. We were told to ignore drag because it would be too small to be significant. Here is our position versus time graphs. Notice the y equals the x is going to be our slope. For each of these, notice how the slope is the largest in the vegetable, or is the smallest in the corn syrup, and the largest in the isopropyl alcohol, largest in the negative direction. These are velocity versus time graphs. Notice how they are almost all linear. The velocity versus time graph for the vegetable oil is pretty linear. It just has a smaller scale than the velocity versus the isopropyl alcohol. And the slopes from these graphs are the acceleration, which are very near zero, indicating that there is no net acceleration, no net force. These are our calculated viscosities, our largest being the corn syrup at 144.88 kilograms per meters per second, and the smallest would be the isopropyl alcohol at 1.5 kilograms per meters per second. These corresponded with the slopes for our position versus time graphs, leading us to believe they are directly correlated. For this experiment, we conclude that the higher calculated viscosity will lead to a smaller terminal velocity. This is because when dropping the balls from the same height, the more viscous solution will have a greater upwards force, decreasing the net force downwards. We believe that this is because the larger molecules have a larger density, such as the molecules in corn syrup. They will push up on the object with a greater force than the object with a less mass and volume, such as the isopropyl alcohol. The result of a larger upwards force will not only cause the ball bearings to reach terminal velocity faster, but also cause the terminal velocity to have a smaller negative value. This is some of the possible error that could have occurred. The main one was being that the corn syrup had over 200 clicks, and some of them could not have been as precise as the others. We believe that this caused a small bump in our graph as seen. Another thing is we would have increased the height of the graduated cylinder, so we would have had more data points to help us analyze the terminal velocity more accurately.